the nature of signals. That's a signal. And the nature of systems. That's a system. So there's an input, and then there's the system, and then there's the output. So, the system takes in a signal and transforms it into another signal. Alright, that's all. This is all that we're going to talk about in this class. What are these signals and how does the system turn an input signal into an output signal? What I do is, on the very general scope, follow loosely Dennis Freeman. At MIT, his lectures are all in the syllabus, so I highly recommend that you watch them before you come to the class. Okay? So that you are prepared. As we have said last year in the introduction, what I expect from you is come to the class prepared. Not try to learn from me, but discuss stuff with me. Okay? I want class participation. I'm not going to just stand up here and write on the board, but I'm going to discuss stuff with you. Is that clear? And of course, I'm going to be asking you questions. So if the class doesn't participate, what's going to happen? Good. All right. The first hour, we're going to try. See if the class has prepared. If yes, we will continue. If not, what's going to happen? Good. Quiz. All right. So, as we always say, do not be a, like we say in Turkish, öğrenci, or like they say in Arabic, talebe. I want you to be students who study. Okay? And study before coming to class. Deal? This is yes. This is no. Deal? Oh, nice. Excellent. Alright. Last week, the first signal that we mentioned was the delta duality, shown as delta of t and described as equal to 1 if t is equal to 0, 0 if t is not equal to 0. Alright, that's a hypothetical signal. It doesn't exist in the physical world. Because if any signal at time equals 0 arrives at a value of 0, it's impossible to rise it to any value, let's say 1, in 0 time. Physical systems have inertia. They resist a change in state. Okay? So you have to overcome that inertia, and that takes time. So normally in a physical system, this is what happens. The signal comes to the value of 1 in a finite amount of time, let's say delta t. But we're going to assume that it takes 0 time for the signal to get to a point. Alright, that's, like we said, physically not possible, but mathematically we can imagine it. And once we imagine it, we can use it. And when we use it, it helps us a lot in mathematical constructions, in our modeling of the system and the signal. So the delta is something like this. This is the origin. Let's assume that a signal starts at minus a, time equals minus a. Alright, rises hypothetically to a value and ends at time equals plus a, back to 0. Okay? This we call a square signal, square wave. And the intensity of the signal we will assume to be 1 over 2A. Okay, so that the area is going to be this length, 2A, times 1 over 2A, which is equal to 1. So, gelecekseniz ne yazın lan? Manyaklar, orada bakıp maymun mu olacak? İnsanlara maymun demek üstün. Yok, siyah dersen çocuktur, beyaz dersen değil. Türkiye kamuoyunun tartıştığı olay var. Okay, so what happens is I'm gonna make that signal start at some earlier point. Okay? So this is gonna be minus A is gonna be greater than, let's call this minus B at this point. Okay? Negative sign greater than, it means that in absolute value, B is greater than minus A is less than. Okay, minus B is greater than A. So therefore, the B is here, closer to the origin than A, in absolute terms. And ended at plus A. Okay, so in order to keep the area at 1, this height has to be larger than 1 over 2A, obviously. Okay? So the area is still equal to 1. It has to be equal to 2B, 1 over 2B, still equal to 1, with absolute B being greater than absolute A. Right? Plus or minus, they are larger. So the trick is to keep the area at 1. And as I keep this closer and closer to the origin, I'm going to approach 0 thickness. Right? And in order for, since the thickness is 0, then this has to be infinite. Because if B is 0, 1 over 2B is going to be infinite. Right? So this is going to be in the limit as A approaches 0, or B approaches 0, or any other letter. This is going to be 0 times 1 over infinity, and that's indeterminate. Right? 0 over infinity is undetermined. But theoretically, we are going to assume that this is equal to 1. Right? Because if it's not 0, but very, very close to 0, and this is not infinity, but very, very high, right? Then we are not at undetermined state. We still have a finite state. And that state area is still 1. Okay, so in the limit, that area as A approaches 0, both from the minus and from the positive side, okay, is going to end up being 1. You get that? So I'm just making it narrow to keep the area, it becomes higher. Narrower, higher, narrower, higher, so that the area stays the same. So in theory, the area of delta is 1, and the magnitude of delta is infinite. So this is 0 and goes to infinity. But I don't want to deal with infinity, so I normalize it to 1. Okay, so the theoretical delta Dirac has a height of 1 and a thickness of 0. Okay? Anybody not understand this? Narrowing it, making it higher. In the limit, 0, infinity. Normalize it, 0, 1. Okay? That's the theoretical delta Dirac function. We're going to use this a lot. This is we're going to call impulse. An impulse is like a kick, no time. Infinite force. Doesn't happen. Mathematical possible. So it's an impulse input. And since the height is 1, we're going to call it unit impulse. Okay? Another type of input is the unit step function. Unit step, gel. Niye geç kaldın? He? Hayır. Niye geç kaldığını cevabı kusura bakmayın hocam değil. Neden geç kaldın? Değil mi? Daha önce geçeceğiz. Alt köşeye daha önce unit step, the same thing happens with a signal coming at 0 value, and then when t equals 1, it goes up to 1 all of a sudden. Is that possible? Who is coming? Is this possible from 0 to 1? Any signal? In no time.
It's not
I
possible.
can't hear you.
It's not possible.
Participation is fine. So, this is also a theoretical signal. It doesn't happen in real life, but we're going to use it in mathematics. And the difference between unit step and unit impulse is that unit step stays on. Alright? Forever. At 1. Okay? And we're going to call this as U of t. Unit step. And that's going to be equal to 1 if t is greater than 0, and 0 if t is less than 0. And since it's also equal at 0, we put the equality sign. Alright? It hits, it strikes, Türkçesi çakmak. Çakıyor nerede? 1'de, ama 0'da. It strikes at 0 time and goes on forever. What's an example of that? For example, if you have a circuit, a simple RC circuit, the current here, if the circuit is open, is 0, but once you close it, it's going to be 1, or B, or whatever that R is. Okay? So, or a constant. You turn it on at time equals 0, it starts giving you Q. You turn it at time 0, it starts giving you R. Before that, it's not for. Okay? Alright. Or it's a spring resting there by itself, not doing anything, minding its own business. At time 0, I start pulling it down with a force F. Okay? So the force or the input is turned on and stays the same. That also is not possible, of course. Because when I start pulling it down, I only pull it down very little, in infinitesimal amount of time, dt. So therefore the distance here is dx, infinitesimally small. Okay? And an infinitesimally small distance is only caused by a force of k times dx, k being the spring constant. Okay? And as time increases, 2dx, 3dx, 4dx, 5dx, as I keep pushing, I'm pulling on it, the force increases. So I end up something like this. Alright? But theoretically, I'm going to assume that who can do this? Who can do this? God. Can we humans do it? No. Good participation. Alright. So we're using mathematics And mathematics is the language of God. Who said that? You said it? You said it? No, somebody else said it before you. Anybody know? Remember from introduction? Who? You said it? Did you say that? Yeah. Good for you. Alright. Galileo said, God has written the book of nature in the language of mathematics. Alright. So whenever we use mathematics, we're doing approximations. Circle. Does a perfect circle exist? No. A point. Non-dimensional doesn't exist. A line constituted of points. Does it exist? No. But we can use the language of mathematics to imagine that it is there, to use it in our calculation. So here we're not doing anything out of the ordinary actually. We've been doing it all the time. The moment we start using mathematics, arithmetics, whatever, geometry, we've been doing using God's language. Okay? Alright, so these are only the approximations. Another signal is ramp. And ramp R of t is equal to t, that's t is equal or greater than 0. And 0 if t is less than 0. So at time equals 1, r is equal to 1. Time equals 2, r is equal to 2. Okay? That's the unit ramp. Combining these data, unit impulse, unit step, and unit ramp, we can create many different signals. For example, if you say u of, okay, I have to tell you one more thing before I go. Now we call these delta of t, u of t, and r of t. And then we set this starting point at time equals 0. Why? Because delta of t, when I write delta of t, this here is the argument of delta. Okay? And delta starts when the argument is equal to 0. So, in order to find out when delta t strikes, I have to say the inside of it, t, is equal to 0. Now, if I change this index, time index, to delta of t minus t1, for example, t1 being here, okay, then the arguments by the same logic, t minus t1. And I set the argument to 0, so I find t equals t1. So I say delta strikes at t1. 0 before that, 0 after that. We call that time index. So we can decide when the signal will strike by changing the argument of the signal. So, if I say, for example, delta of t plus delta of t minus tau, another signal I form, call it x. And if I want to plot that signal, then delta of t is going to be striking here, t equals 0, and delta of t minus tau is going to strike when t is equal to tau. Okay? So So that is going to be my x. A signal where I turn the switch on and off, wait, turn the switch on and off. Okay, and then it goes up. Stay at 0. I can increase this. Plus delta t minus 2 tau. Then I add another stripe, 2 tau. Okay, it goes on like that. Now for the unit step, if I say u of t, I'm doing this signal. If I add to this u of t minus tau, okay, then at t equals tau, I'm adding another on top of this, so I have to add them up. So I get this. Right? Then another step. If I add, for example, u of t to minus u of t minus tau, then my signal is going to be u of t, and at the point of t equals tau, I'm adding this. Okay? So this signal plus that signal is going to be 0. So the net signal is going to be that. Okay, so by adding the signals, the basic signals together, you can create more signals. Any shape that you want. For example, if I want u of t plus r of t minus tau, I'm going to have a u of t, and I'm going to add to this a ramp that starts at t equals tau. So when I add these two signals, I'm going to end up with a signal that goes up to tau is a unit, and then starts going up. Because after that point, I'm adding the two signals together. I'm adding the two signals together here as well, but the second signal is 0 at that point, so I only have this. Yeah. Things like that. Okay. So, for example, exam question, how do you create that signal? Or how do you create a triangular wave? Okay, you have to work it out. Use your imagination to have additions of plus or minus delta unit step and unit ramp. Okay, you can do many signals, create many signals with the combination of these basic signals. Okay? What you can do is you can say if you like for example, this will be a ramp combined with a negative ramp. Okay, until tau. And then after tau you add a negative ramp. After 2 tau you add a positive ramp. And then a negative ramp. So you go on like that. Okay? You may want to say t plus tau. T minus and tau. To that. So it's repeated at every end. 2, 3 tau, all the way to n tau. What you can do is t minus n ramp. You add it to a ramp signal. So another thing that I can do is I can create a square wave here at tau and 2 tau. Okay? And then I can say for this signal, tau, I had to subtract. Now if I put u of 2t minus tau minus u of 2t, t minus tau, 2 tau. Now what I'm going to do is I'm going to narrow that signal. If I divide the t divided by n, then I'm going to expand the signal. So we can narrow the signal, expand the signal, turn it into negative, you can turn it into positive, you can make combinations of the signal. Alright, all of this is explained in the syllabus. Okay? Several different types of manipulations with signals. And I said these are the basic signals, but they are not limited to those. We also have the exponential signals. X of t is equal to e to the at. So I create an exponential signal. If I say x of t is equal to e to the minus at, then I create a decaying exponential signal starting from I don't know where, for example here, and going down. Starting at 0. I can multiply it by 2 to expand the signal, to narrow the signal, divide it by 2 to expand the signal, and so on. What I can do is x of t could be 1 minus e to the minus at. Then I have a signal like that. So you need to learn how to play around with basic signals. Okay? As an exercise. And all those exercises are given in the syllabus. Okay? So I'm expecting you to study those using the exercises that either Görkem Hoca, for example, or İsmail Hoca, right? I have added their slides into the syllabus. Okay? The importance of Ismail Hoca's slides is that you're going to use the knowledge you learn in this class, Signals and Systems, and use them in the next year in signal processing class that he gives. Okay? So you better learn the applications of what you learn in one class so that you are more comfortable next year in Ismail Hoca's class. Okay? That's what becoming a professional student means. You have to learn how to study to get a good grade in a given course. And what is that? The tactic to come prepared by any means necessary. Go on the internet, go on YouTube and say signal manipulations. Creating signals with basic signals. Use any keyword that seems logical to you, okay? And get yourself prepared for the exercises that you're going to face in this class. Alright, having said all this, you can go on to sinusoidal, this is exponential. Sinusoidal signals. This doesn't mean that it's only a sinus, it could be a cosine as well. We mean by sinusoidal, we mean periodic signal. Okay, it could be a sine wave, it could be a cosine wave, it could be cosine 2t, for example, you squeeze it. Or it could be cosine t over 2, you expand it. Okay, you can manipulate those signals. You can add a unit step, you can add a unit pulse, can make all sorts of signals with those. And then there are random signals. Okay? Random signals, not that random, but for example, combinations of an exponential and a cosine. Okay? That means that you have a cosine here, and then you multiply it with a decaying exponential. So you end up with this, just like the second order response of the system. So you can multiply signals together. You can add one cosine to another cosine. Okay? So one cosine is going to be something like this. One cosine is going to be something like this. The other cosine is going to be a different amplitude and a different frequency. So what you're going to do is when you add these two signals, you're going to have some signal that is like something like that. I don't know. Alright? A complex. Not easy to recognize signal. So signals can be added on top of each other, can be subtracted from each other, can be multiplied with a scalar, can be divided by a scalar. Okay? So you have to be prepared to face all of these signals. Now, one good thing about the complicated signals like that, sinusoidal signals, is that they can be expressed as exponentials. In order to explain or expand a sinusoidal signal, omega t or a sine omega t, with an exponential, you have to go to the complex domain. We have talked about Euler's equality, remember. Euler's equality says e to the j theta a angle is equal to cosine theta plus j sine theta. Okay, this is Euler's identity. If you don't know what this is, study and learn again on the internet or wherever. I'm going to give you a little introduction here, but I'm expecting you to know what a complex exponential is. Of course, now we're talking about complex signals. Complex signals that have an imaginary part and a real part. Okay? So in order to express that complex signal in a more visually understandable way, what we can do is we can go to the complex plane with an unit vector I on the real axis and an imaginary vector, unit vector J, on the imaginary axis. The size of I, since we call it a unit vector, is shown by this signal, this sign. The size. Okay? Whatever I put in here is the argument of this. This means the magnitude. Alright? The magnitude of I, for example, is 1. Because it's a unit vector. Now we have to understand, you're taking linear algebra this semester, we have to understand what a vector is. So as as you can see, one idea is going to require you to understand another idea. And that idea is going to require you to understand another idea. Okay? So the foundation of this knowledge is really large. And that's why I'm saying you have to be prepared for understanding what's going on in this class. And hopefully that information has been given to you before. We're just going to go over that little bit here because we have more important business to deal with. Now the vector I and the vector j, the number j being a complex number equal to square root of minus 1. Again, a mathematical imaginary number. It doesn't exist in real life. It's a mathematical tool, only in God's mind, that we use to make our equations and calculations and everything much simpler. Okay, that's a paradox here. You're using a complex number to make your dealings simpler. Okay? The beauty of the complex numbers, we're going to see in a second, is that you start with them, and then along the course of the calculations, they cancel each other. So, from a real system, you go to an imaginary system, and then they cancel each other, so you go back to the real system. But in the meantime, you solve your problem. So the imaginary plane, the complex plane, is just a domain that we visit to make things easier for us. But you cannot live there. You cannot stay there because it's not real. You have to go back to the physical world. Alright, this is the physical world. This is the physical world. But to solve a complex problem in the physical world, we go to the easier, complex, or mathematical world. This world we say domain. Alright, the real domain and the complex domain. Why? On the right side of the right hand side of God. Okay? You can visit there, but you cannot live there for long. Any questions so far? Who's going to take time for it? Keep time for it. You want to keep time for it? Oh, you must be crazy. Right. So what is the deal with keeping time? You tell me when there's 10 minutes to the end of the class. You warn me. Right. And then you say, class is over. Right. And usually I'm going to be right in the middle of explaining something beautiful. So when you say, you have 10 minutes, I'm going to be really upset. But don't take it personally. Right? You're just doing your job. Your voluntary job. So what time is it? Remaining minutes. Oh, so that I can hear you.
13 minutes left.
13 minutes left. So when are you gonna, in how many minutes are you gonna warn me?
2 minutes.
How many? When is the first warning coming?
2 minutes.
Huh?
2 minutes.
2 minutes left. What time is it now?
48.
14.
48.
48. Oh yeah, so 2 minutes left to the break. Alright. Okay, so we talked about the complex plane with the two unit vectors. A vector is a quantity that has a magnitude and a direction. Okay? The magnitude, for example, vector S, is the magnitude of S, direction of S is the argument of X. Okay? Direction means argument. Later, you can also call it phase, or the phase angle. So, a plane, let's say a two-dimensional plane, alright? We can use the two-dimensional plane to indicate the location of any point on that plane. Okay? On that plane. The location of any point P on that plane. We can use the coordinate axis, which we call Cartesian coordinates, or we can call or we can call polar coordinates. Let's continue with that in the next hour. We'll come back to the top of the hour. Who came to class? Who came to vectors and all that? Business with vectors. Vector has magnitude and direction. Those two things characterize a vector. Alright? In a coordinate system, a perpendicular orthogonal two vectors, unit vectors, in the imaginary, one in the imaginary direction, one in the real direction, is enough to characterize the whole plane, two-dimensional domain, the whole thing. We call that the complex plane. And any point on the surface is called S. Okay, has an abscissa. We call sigma. Açalım. Aynen. Çok teşekkür ederim. Bunu da almanızı tabii daha yukarı vazgeçilmez elemanlarından biridir. Saadetine ait olması lazım. A real component, abscissa, and an imaginary component, omega, on the ordinate axis, is enough to give us the direction of any point, not the direction, the location of any point. Now you need to understand that this sigma is a scalar. A scalar means that it's a constant number that scales a vector. Well, that's all. That's what a scalar does. And scaling means either to make it longer or make it shorter. Okay, that's a scalar. So if you multiply a scalar with a vector, okay, you create another vector that is longer than or shorter than this in this amount. And you call here. Right? So that would be sigma I. Here. And then this would be then omega j. This vector here, omega j. So by vector addition, we can form the vector S. Okay? Now what that means, you probably know this, but I'm going to go over it anyways, in maybe hopefully new terms. In order to get from the origin to the point of interest, S. Now S is the vector here, and S is the point here. Any point can be turned into a vector by connecting it to the origin. Okay? So in order from the origin, to get from the origin to the point S, you have to go in the direction of I, this direction, the real axis direction, sigma units. And then stop there and then turn 90 degrees in the direction of J unit vector. Okay? So by this token, you can describe any point on any quadrant of the plane. Okay? Now remember, if you're not taking notes, I strongly advise you to take notes because anything that I mention in the class means that you need to learn it. Okay, these are words, not because I'm going to ask them in the quiz or I'm going to take away your points, but these words or concepts you're going to be using from now on. Alright, in everything that we do, as far as engineering is concerned. If you're dealing with signals, you're dealing with systems, you're dealing with, whatever, biological systems, you have to learn these terms. You're probably learning this in linear algebra, but anyway, it's good to repeat. So, in a, for example, third quadrant, okay, both sigma and omega are negative. Obviously. Sigma, omega. Negative. Alright? In the first quadrant, both are positive. In the second, omega is positive, sigma is negative. Alright? So on and so on. So, by assigning various values to these scalars, you can define the vector, and through the vector, you can define the point S. And remember, this is a complex point. Alright? This is defined by sigma and omega. The coordinates. The vector itself is a combination of vectorial combination of two vectors. To combine two vectors, you have to add them head to toe. Alright, go this way and start from the toe of this, go up. For example, if you have two vectors like this and like that, alright, what you can do is, as long as you don't change the angle, which is the argument, the phase of the vector, which is that, and here it is that, and you don't change the magnitude, okay, you can shift them. So in order to add these two, you have to bring the head of one to the toe of the other. So move it like that, move it like this. So this is it's going to make the vectorial stop. So you start from the toe, go to the head. Alright? So if this is omega x, vector x, and this is vector d, u and d, let's say, this is going to be u plus d. Okay? So the vectors can be moved, shifted in space with the complex or the real plane, as long as you don't change them. You don't scale them, and you don't change the phase. Alright, so here we're just adding this vector to that vector to obtain their sum. Okay, now there's another, this is the Cartesian coordinate system. And Cartesian comes from Descartes. He is the first one to bring geometry to mathematics. Okay? He expressed mathematical quantities in geometrical form so that we can visualize them. Humans are visual animals. Okay, so if you say this, well, I may understand it, but if you say that, then I definitely understand, right? Because I'm a human being. I'm not a monkey. Although it's not boring. Okay. So there is one description of the address to the Cartesian coordinate system. The other one is the polar system. So I'm trying to define a vector like that with an angle and a magnitude. Okay? So first I put this vector here, not changing the magnitude and the angle. I translate it to the origin. Okay? Then I take the projection of it and get this thing, the projection. Okay? And then I rotate it by that. By that angle, I get this thing. So I end up with a shorter way. Okay? So that's not a good way to do it. What you need to do is then to keep the magnitude as well. Okay? Take the perpendicular projection of this vector here and then rotate it by the angle. Okay? So the magnitude of this S and the magnitude of this are the same. I am first giving you the magnitude, and then I'm asking you to rotate it in the direction of the face. Okay, so the way I show this then is S is equal to magnitude of S and the argument of S. Both of them are going to get me to the same point S through this vector S. Okay? I can either use the Cartesian coordinate system or the polar coordinate system to define a vector or through a vector a point. Questions? I think everybody understands. Spectacular. Like Trump says, fantastic. Okay. So now that we have a complex, one of the unit vectors is a complex vector here. So that therefore I have a real part of my vector and the imaginary part of my vector. Okay. And the convention, by convention we means con together. Convention we talked about this always. To come, to get, and this is the act of. So to come, the act of coming together, the way that people agree to describe something by convention, we are not writing the I to describe S. We are not writing the I because it's a unit vector and it's real, so who cares? We are only writing plus omega j. And we don't even put the vector here so that this is not a vector either. That's the point. Okay? If I put the vector sign here, then this is a vector, and I have to put a vector sign here. Okay, well, I'm going to describe a point now. So sigma is scalar plus another scalar multiplied by the complex number j. And again, by convention, we put the j in front of omega. Okay? So the complex number S is described as sigma plus j omega. That's your complex number S. So, to repeat, a unit vector on real axis, another unit vector, but a complex vector on imaginary axis. Unit and unit vectors, both magnitudes are 1, and they are perpendicular to each other. Perpendicular means ortho. Okay? Ortho means perpendicular. Gon means, for example, corner. Orthogonal means that has perpendicular corners. Okay? Instead of gon, which is Greek for corner, we use gan. Üçgen, for example, 3 corners. Okay, and the Italians said this is a Turkish letter, but in Turkish word, it's not a Turkish word, it's just an adaptation from Greek. Alright, so these two vectors are orthogonal to each other. and they are unit vectors, which means that their magnitude is both 1, magnitude of j and magnitude of I, both 1. Okay? And if the magnitude is 1, then we call that normal. So we're using an orthonormal combination of two vectors. And when a two-vector combination like this defines every single point on a plane, we call them a basis. So the ij vectors form an orthonormal basis for the complex plane. Okay? And by using the convention from the abscissa and the ordinate of the vector, we derive the complex number S. Right? S equals sigma plus j omega. We're going to be using this a lot, okay? Now imagine that you're on an orthonormal complex plane. Now, we're talking the same language, okay? You must understand what I'm saying. Orthonormal complex plane. What do you understand? Both vectors are normal, orthogonal to each other, and they form a basis for the complex plane. Complex plane, therefore, one of them is a complex vector. Okay? So, when I say on a orthonormal complex plane, okay, imagine that we have a vector of length 1. Okay? Well, actually, that's not 1. I'm sorry. We have an, this is 5 equals 1, and this is j equals 1. Okay? And imagine that we have a circle. One is 1, and the other one should be 1 as well. Okay? We draw a circle along these vectors, okay? Just changing the phase of 1 to 90 degrees, and then another 90 degrees, another 90 degrees, and another 90 degrees. So what we say is that the norm of this radius now is also 1, okay? The radius of the circle. Therefore, the circle is a unit circle. Okay, just like unit step, unit impulse, it's a unit circle. On that unit circle, any point S on that unit circle with an angle for phi, okay, with an angle for argument phi, and a magnitude 1. So our S vector is going to be 1, 5, okay, in polar coordinates. And in Cartesian coordinates, it's going to be cosine phi and sine phi. So sigma of S is going to be cosine phi, and omega of phi is omega of S is going to be sine phi. Everybody follow, right? Nothing new so far. So I can describe this point as cosine phi I plus j sine phi. Okay? According to this convention, then, I'm going to remove this I describing the S vector in terms of its Cartesian coordinates. And I'm describing the S vector in terms of its polar coordinates. The two are the same. Okay? All right. Now, if R is not equal to 1, but is equal to any number R, right, then my circle is no longer going to be a unit circle. Any vector, let's say the same phi, right, is going to be now R cosine phi plus J R sine phi. So I can put this in parentheses, cosine phi plus J sine phi. Okay? And now I can define this vector as R times phi. Okay? Now obviously, we said this is sigma and this is omega, the scalars along the unit vectors defining the basis. R is going to be equal to this R, alright, is going to be equal to cosine phi squared plus sine phi squared, square root of. This is the cosine phi, R times cosine phi, and this is R times sine phi. Okay. Sorry. R squared is going to be 1. It's going to be R squared. The obvious is I can take R squared out, cosine squared phi plus sine squared phi. Okay? R squared goes out the top, that's going to be R. So this is 1 as you know. So I can describe any vector on either the unit circle or any arbitrary circle, okay, in terms of this trigonometric identity. The other thing that I can do is I can pretty much use this thing and represent it as Euler's identity. This is representing the vector in Cartesian coordinates. This is representing the vector in polar coordinates. This is representing the vector as a complex exponential. If you're not on a unit circle, then I simply multiply it by R and multiply this by R. Okay? So a vector in the unit, in the complex plane, can be either expressed in polar coordinates, in Cartesian coordinates, or in complex exponentials, in terms. And how is that possible? How did Euler come up with this? Well, this is how Euler came up with this. He looked at e to the j I, okay, and took the Laplace transform. And obviously, the Laplace transform of this is 1 over s minus remember. Exponential Laplace transform is x minus j prime. Remember that, right? Who doesn't remember this? Who wants me to show this and prove it? That Laplace transform on an exponential is this. You don't know how to do it. Who else? There's already one, two. Who else? Okay, so one comes up, many people come. It's a crowd mentality, crowd psychology. So the definition of x of t times Laplace of any function is integral 0 to infinity x of t times e to the minus st dt, right? You remember that at least. Okay. So if you put e to the j omega here, e to the something, let's say at, then let's say x of t is e to the at, e to the minus s dt, according to the formula. I'm trying to find the Laplace transform of the exponential. And şu arkalarda ses çıkmasın arkadaşlar. And since Laplace is scalable, then if x of t is any scalar here, then I just put it here, right? I can scale it. So anyway, that's going to be from 0 to infinity. I can put this as a to the minus s minus a1. Okay, so minus s minus a. Okay. And the integral of this is a constant, this is a constant. The integral of any exponential is the exponent itself minus 1 over s minus a times the function itself, e to the minus s minus a t. And now I have to integrate it from 0 to infinity. So I put 0 to infinity here. And that's for minus 1 over s is here. And parenthesis e to the minus s minus a infinity minus that's what it is. Minus e to the minus s minus a 0. Alright, this is going to be 0. It's going to be 1 minus 1, so therefore you're going to have 1 over s minus a. If whatever a is here, you put it here. If this is plus, then go to minus. If it's minus, you end up with a plus. Okay, so the Laplace transform of a complex exponential, whether scaled or not, is this in S domain.
How is the j prime a not omega j squared? Actually, it would be s minus j.
Now this could be anything. It doesn't have to be t or anything. I'm just taking the integral of this with respect to t bar. Here there is no t. Alright, so there is only this constant. Okay, so I'm taking the Laplace for this, only with the constant. Okay, not with t or anything. Whatever you have up here shows down there. If you want, you can put t. So that's it. Is that better? And now, when we have the imaginary number of the body, we don't like it in complex algebra. Are you doing complex algebra differentials? Or you started? This is yes, this is no. Have you started complex algebra? Sen şuraya koyuyorsun. Wake up that night. Wake that night. Uyuyacağım mı bebeğim? Yok hocam ya. Hadi git dışarıda. Kahveyi sadece aldınız mı? Almadınız değil mi? Eğer yere bakarsan sorularını duyamazsın. Bütün sınıf senin yüzünden gözükür. İster misin? Yok. İstemezsin değil mi? O zaman bana bak, olur mu? Yere bak. Anne sana söylesin, o üçüncü ayeti galiba. Erkeklere ve kadınlara yere bakmaları okay? Ama biz sınıftayız. Exception yapabiliriz. Yere bak. Bana bak. Uykun varsa hiç. Hocaya saygısızlık etmeyin. Biz burada terk ediyoruz. Sizin için. Okay, so if we have a J on the bottom, now what we do is multiply this top and bottom with its conjugate. Now when I say conjugate, I'm assuming that the conjugate of any vector in the imaginary plane. Vector with the magnitude and phi is a vector with the same magnitude but a negative. So the conjugate of that vector would be, for example, minus this, and that would be its conjugate. So the conjugate of that, and understand that we are keeping the sigma the same, but changing the sign of the omega to get the conjugate. Okay? So the conjugate of S sigma plus J omega is sigma minus J omega. Okay? And if this is S, for example, we show the conjugate with an asterisk. Okay? So what I do here is I multiply the conjugate of this top and the bottom. And if I have a minus multiplied with a plus, A minus B times A plus B gives A squared plus B squared. Okay? This is going to give me on the bottom S squared plus J minus J pi squared. Okay? And that's going to be on the bottom S squared minus J squared and pi squared. And that's going to be on the denominator S squared minus 1 pi squared. So that's going to be S squared plus pi squared. So I'm going to immediately get rid of this J on the denominator. Thank you. So on the top, we have S plus J pi throughout. So this is S plus J pi. Okay? So if this is the common denominator expression, I can separate this S squared plus pi squared plus J times pi divided by S squared plus pi squared. And this is the Laplace minus. So if I take the inverse Laplace of this whole expression, okay, with S on top and pi on top, S squared plus pi squared on the bottom, S squared plus pi squared on the bottom. Laplace being a linear operator, I can use superposition. So this is going to be L minus 1, S divided by S squared plus pi squared plus L minus 1 pi over S squared plus pi squared. And that's going to give me cosine here and J sine there. Cosine phi plus J sine phi. So that's how Laplace came up with this, alright? Euler came up with this equation. And the dynamicity is extremely important for us. Not only important, but also it's beautiful. Have you heard of Feynman? Richard Feynman, excellent. Richard Feynman says that, believes that this is the most beautiful equation in mathematics. Why, they asked him, and he says the following. Since e to the j phi is equal to cosine phi plus j sine phi, alright? If I put phi is equal to minus phi, okay? Then I have e to the j phi e to the minus j phi is equal to cosine minus phi plus sine minus phi. Cosine minus phi is minus 1. J times sine minus 1 is 0. So the end of it, we e to the minus j phi is equal to minus 1. And we turn this into e to the minus j phi plus 1 equals to 0. So that equation has constant e, the constant pi, the term j, complex number j, minus and plus signs, equality sign, okay, and 1 and 0. It has every single formula that we use in mathematics. It's a beautiful, beautiful formula, such a beautiful expression. Very simple, yet extremely elegant. Alright, so we show a complex number or vector either with S equals sigma plus j omega Cartesian, or a vector magnitude and the argument, or r times e to the j phi, okay, with polar coordinates and with complex exponentials. So we have three ways of showing a complex number on the complex plane. And as you can see, we're going to use these complex exponentials, complex algebra, vector algebra, anything that you can think of in mathematics and geometry and complex algebra, we're going to use in this class. Right? So you have to be pretty good in those manipulations. All right. So what we have done, what I want you to do is first learn the manipulation of basic signals. Right, like delta, U, and R, adding them, multiplying them, contracting them, expanding them, okay? And then remember the Laplace transform, because I don't want to repeat it in this class, but the basic formula is this number. And then if we put it here, you're going to find the answer. For example, for homework, you can find out that the Laplace of cosine anything is phi divided by s squared plus phi squared. Actually, s. Ciao, passation. vector representation. Of complex numbers and okay, in order for you to stay in the class, understanding everything that we say on a timely basis in the classroom, because that's the best way to learn, alright? Just take my word for it. If you lose me in the classroom, if you get lost in the session way, then it's going to be extremely easy for you to catch up later on by yourself. The best way is to understand me when I'm giving the class. And if you don't, at some point you miss, stop me, okay? There's nothing wrong with that. I can explain it again and again and again until everybody understands. Okay? Don't be afraid of starting and asking questions. Is it coming?
Sir, can you fix that one and suppose the airline skills and custom is recognized?
Thank you. Such an attentive young lady we have amongst us. Okay, what time is it? 2 minutes left. Oh, I can spell like actually I'll have to do backwards for 2 minutes. So, next hour, what I want you to do is start talking about, so far we've been talking about signals. And how is this S a signal? Well, because S comes in here. Exponential. Exponential is a signal. So we have to learn complex exponentials as signals. And that's going to be extremely important in 2 classes. We're going to learn a very important property of complex exponentials given to signals, given to systems as input. We're going to find out about that and we're going to use it a lot. Okay? But for the time being, this is so far with signals. Okay? That's extremely important. And now I'm going to talk about systems ability. Okay? For the third hour. Alright, let's read and talk about the They have a certain job, but they work in harmony together. And their job together is to convert the signal, input signal, into an output. The components, depending on the system, could be MAD, mass, swing adapter, or inductance, capacitance, and resistance. Or it could be the area of the reservoir, the hydraulic resistance, and the hydraulic mass. Alright? And they are not the same element, but they each perform the same job. We call that analogy, system analogy. So, for example, if the system is mechanical, then we have a spring, a damper, and a mass hanging by the mechanical ground. This is the ground. It doesn't move. Subjected to a force in the outside environment. And giving us a reaction, measurable reaction. In the mechanical system, this is usually the distance x by which the system moves. Alright? output of the system, or the reaction of the system, or the behavior of the system, or the output of the system, in a mechanical system, obviously, is measured by the derivatives of the distance. If it's an electrical system, in the mechanical system, the output is x. In the electrical system, the output is the charge. And the hydraulic system, the output is the volume. Okay? So when you pour fluid into the reservoir shows you an increasing volume. If you take fluid out of the reservoir shows you a decreasing volume. That is the output of the hydraulic system. If you give voltage to the system shows you a charge filling the capacitor. Okay? If you're applying a force to the mechanical system, then the system is showing you a distance. Okay? Each of the components has a duty. The spring stores potential energy. The damper dissipates heat energy. And the mass stores kinetic energy. In a mechanical system, if we input force in it, then the mass is going to accelerate. The spring is going to expand. And the damper is going to dissipate the heat. These are coefficients of the components. The systems that we're going to be dealing with in this class are going to be called linear systems. They're going to have constant coefficients. Okay? They're going to have an external force on it or not. Depending on if there is a force, we're going to call it a non-homogeneous system. Or if there's no force, but it's only acting as a reaction to the initial condition, then it's a homogeneous system. You should remember those. And their behavior is going to be expressed in terms of a differential equation. In order to arrive to the differential equation that shows the behavior of the system, we have to start by establishing a force balance. Of course, I'm talking about a mechanical system here. Alright, if it's an electrical system, then we're going to establish a voltage balance. Or if it's a hydraulic system, we're going to be talking about a pressure balance. So what we're going to say is this external force is dividing itself, just like a river splitting into branches as it encounters obstacles in front of it. this force is going to express itself on the mass according to Newton's second law, on the spring according to Hooke's law, and on the damper according to Hooke's law again, but that's disputed. So what we're going to say is this force is going to be opposed by an inertia F of the mass, the portion of this external force that is distributed over the mass. Okay? This is to overcome the inertia of the system. And inertia is expressed in terms of mass. Inertia means resistance to a change in the state of the system. For example, you in the morning are sleeping in bed and you have a hard time getting out of bed. You don't want to change your position, your state. But at night, you're awake and you have a hard time going to sleep, going to bed. All right? You don't want to change your state. When you're in the morning, you're about to ready to take your bath. You don't want to go into that shower. But once you're in the shower, you don't want to get out of the shower. Okay, so you are putting a resistance. Same token, a mass is going to resist my push. Alright? I'm going to have spend some of that force to overcome that inertia. That's the mx double dot component, ma. Okay? The spring is going to react to the external force by showing some stiffness, which we expressed as in terms of that k, f equals kx. Okay? And the damper is going to show resistance to your velocity. The faster you push the system, the stronger it's going to resist, just like in a bicycle pump. Right? The stronger you push it, the more resistance you're going to feel. But if you go very slowly, then there's almost no resistance. Okay, so those are the things that these components do. Alright? So what I can say is that the external force is opposed by this force, and by this force. Force of the damper and the force of the spring. Okay? And since the summation of the forces are always going to be equal on the system, we can write summation of the forces is going to be equal to F external. Right? If I show the direction positive this way, then force external is going to be positive, and all the other forces are going to be negative. So minus mx double dot plus bx dot plus kx. Alright? That is going to be 0. Yes?
This might sound a bit silly, but I was wondering if this course also deals with like the togetherness of mechanical and hydraulic systems, for example.
Of course.
Yes, we're not just going to take them separately. And if, like, for example, if we consider systems that have both mechanical and hydraulic components, is that dealt with also with differential equations, or is there like a more advanced mathematics in there?
No, it's always differential equations in terms of a hydraulic system differential equation plus mechanical system differential equation. Or you can express the hydraulic system as a mechanical system using analogies. Instead of m of the mass, you can use the mass of the water. Alright? Or instead of the mass, you can use the inductance of the inductor. That's the beauty of analogy. You can move from one system to the other using mathematics, mathematical quantity. Okay? So here what I do is that I put this on the other side, mx double dot plus bx dot plus kx equals f external. So this is the non-homogeneous part of the system, and this is the homogeneous part of the equation. Non-homogeneous part of the equation, I apologize. The homogeneous part means there's nothing but the system. Non-homogeneous part means there's addition to the system from the outside, which is the outside force. Alright? And that force is going to cause the motion, is going to cause the distance, and it's going to cause the acceleration of the system. Okay? You are putting an effort into the system. And you remember from introduction that energy is force times distance. So d energy is force times dx. And if you get energy by integrating the two, you get F times dx. Alright, so when I say you put force, you apply force to the system, I also mean that you are putting energy to the system. You can express the outside factor that you experience on the system, or that the system experiences in terms of force or in terms of energy. They are interchangeable. Okay? So we said that the system is into motion, but we are equating the forces to zero. What does that mean? It means that we are expressing the motion that the system experiences inside this homogeneous part. Okay? So this doesn't mean that the summation of the forces is zero, therefore the system is not moving. But it means that some part of the force is going into moving the system. Okay? Internally, we are expanding that force into moving the system. The other one into dissipating energy. The other one into storing the potential. So, from the force balance, okay, I move on to the differential equation. And the differential equation has an order, okay, is either linear or not, the coefficients are constant or not, right? It's either homogeneous or non-homogeneous. Okay? It could be anything. It could be working under an initial condition, or there may be no initial conditions, just an outside force. And remember that if there's no outside force, no initial conditions, and the system is not going to move. So if you want to calculate the motion, the behavior of the system, which is homogeneous, that system is not going to move. But if you have an initial condition of that system, then it's going to move. Right? So, if the system is the differential equation of the system, the order of the differential equation, higher, which means there are one dot, two dots, or three dots, or more dots. That means the order of the system is getting higher and higher. And the differential equation is getting harder and harder to solve. So usually what we do is we try to simplify the system that we are dealing with. As a matter of fact, when we talk about a linear and constant coefficient system, we are already talking about a simplification. Because in nature there are no linear systems. Everything is non-linear. In nature, there's no system with constant coefficients. The mass may change. The mass of a car, for example, as the car goes on the road, it expands gas, which is the mass of the system. So the mass continuously decreases, right? Or if you're talking about a spring, when it's hot, the spring is going to get less stiff. It's going to be easier to pull out. Or if it's cold, then it's going to be much harder to pull. It's going to get stiffer. So these coefficients always change. But again, you're doing mathematical simplifications. Okay? To handle the complex physical systems differential equations in an easier, more manageable way. The more assumptions you make on the system, your result is going to be that much erroneous. There's going to be more error in your result. Okay? But if you make your assumptions reasonable assumptions, then the error is going to be small and you can deal with it. Right? Otherwise, it's going to be non-realistic. A response that's going to be totally like, that's not possible. Okay, so you make the complex system in car with spark plugs and with gas pumps and with filters and everything, with the guy and the tires and the exhaust pipe and whatnot. A much simpler, you turn it into a much simpler system. Okay? You make approximations. For example, if the mass of the system is really small compared to the spring stiffness or the resistance of the damper, then you can neglect the mass. Its effective mass is going to be so small that even though there is a lot of acceleration, this term is going to be almost zero. Okay? If the mass of the system is assumed to be much smaller than the other coefficients. So when you do that, you are reducing the order of the system, you are simplifying the system, and in return you are accepting the entrance of some erroneous results into your findings. Okay? But your engineers, for example, if you make a calculation about how much steel and how much concrete you put into a column of the building to support a lot of mass of the building, right? You make a lot of simplifications. This is a very complex system. Even a column, a simple column, inşaatın kolonu, ne kadar demir koyacağım, ne kadar şey koyacağım, çimen. Very difficult actually to realistically analyze and derive the differential equation of this under a force, under the force of the whole building. So you get, for example, an amount of M equals 10 kilograms of steel per meter square, okay, and 120 kilograms of cement per meter square. After your simplification, you know that this is not true. This has errors in it because you made the simplification. So what you do, you multiply all these with a safety factor. Just to compensate for my approximations, I'm multiplying everything by 1.5. Then you put 15 kilograms of steel and under that, I don't know how many kilograms of cement into the column. Right? That covers the error. Right? You always do that, otherwise you cannot deal with the realistic systems. Nothing is linear, nothing is constant coefficient, nothing is as simple as that. Just three components. No way. Okay? Keep that in mind. Engineers always simplify and add a safety factor. Okay? Because the first rule that we have to obey is first, do not harm. Okay? Primum non nocere. Just like the doctors. First, do no harm. Okay? So that's where the safety factor comes in, and we can comfortably run our calculations. So if you neglect the mass, for example, you reduce a second order system into a first order system. So you take care of that with the much easier to solve differential equation. Subject to x at time equals 0, x 0. Now what does that mean? My system doesn't have a mass anymore, it only has a spring and a damper. Okay? The initial state of the system is not going to move. So what you have to do is you have to give it a certain force to begin with, all right, to bring it to that state. If that force is external. So you give into it an initial condition. Okay? And then you take away the force. First, that non-homogeneous, to give it the initial condition, and then remove the force. So the system is going to have some force in it of the spring, which was being equaled by this, so the system was stationary. But now when you remove this, the only force is going to be that, and that's going to start moving the system. Okay? So every initial condition corresponds to a force that was given to it before we start the time. That makes sense, hopefully. Okay? When we say initial condition, it means that we had done something to the system beforehand, loaded it with energy. What kind of energy? Potential energy. Potential energy is F dx, remember? Energy is F dx. So what is x in this sense? K x 0 times dx. Okay, so k is constant. So therefore we have x0 squared, 1 over 2. That much potential energy is loaded into the system, so that when you release it, it's going to try to discharge that energy by moving. Okay? Every system in nature tries to minimize its energy. It's loaded with energy, the moment you let go, it's going to come back to the original state. That's the natural state of the system. Okay? So, whether or not you have an initial condition, okay, if you don't, you need a force. If you do, you don't need a force. Or you can have the force in addition. But if you don't have that force, you must have this to move the system. So when you solve this equation, I hope that you remember, this is going to be another homework for you this week. You're going to remember how to solve the first order differential equation with constant coefficients. We said the system is linear. Why is it linear? Because there is no term in x squared, or x naught squared, or 1 over x, or ln x, anything that makes it non-linear. Alright? We don't have it in here, so that system is linear. An assumption. So when you solve this, then your x of t, alright, is going to be equal to x0 minus f external divided by k, e to the minus k over dt, plus f external divided by k. If you don't, you should study this. Okay, how to derive this. Go back to your introduction notes. Alright? Okay? You need to know how to derive this equation. So that's the system. Motion. The equation of motion. What does that mean? This is how x, the distance, changes with time. In a first order system, if you have an x0, you start with x of t and t. Okay? That's going to come down exponentially all the way to an x steady state, which is given by time at infinity, which goes away, f external divided by k. External divided by K. That's the steady state. What time does it reach that steady state? That's steady state time, which is equal to 4 tau. What is tau? It's the time constant of the system. For a mechanical system, the time constant is V over K. Alright, if you don't remember these, go back to your notes. Next week, I expect you to know this. Okay? It's been a year since you haven't seen this, but you didn't learn it to forget about it. You have to now be able to remember it. Tau means how fast the system reaches steady state. A physical system, you pull it down, you let it go, it's going to go back to zero, or to this. But mathematics show us that it never reaches that. Only an infinity. That's the unrealistic part. Right? Physically, you don't observe this. Why do we have that error? Because we made assumptions. Constant coefficients, linearity, and this and that, and the other. So that we compensate with our steady state time. After this point, we assume that the system is not moving anymore because the motion is so small. The motion is negligible. Right? Any questions? Yes?
Don't we consider inertia in the formula here?
We don't consider inertia because we neglect the mass. We said it's the massless system. Does a system without mass exist? So it's an approximation. To make life easy. Because the second order question, equation is more difficult to solve. Alright? Engineering simplifications, therefore necessitating engineering safety. Okay? Don't forget. If the force is higher, then the system is going to rise. Start from x0, and it's going to rise here at external divided by k. So the system is going to go exponentially rise. And the same thesis applies here. Okay? If that tau is bigger, then the system is approaching that steady state much slower. Okay? So the tau gets here. How do you make the tau bigger? For example, by B over K. To make it bigger, you make a damper with a, you choose a damper with a higher B, so that it opposes the motion. The spring is going to, the moment the spring is going to, you let go, spring is going to move, damper is going to be in motion. Velocity is not going to be zero, so this is going to start opposing the force. To the motion, to this motion. Okay, so if V is high, then the resistance is going to be high. This thing is going to move up slowly. Okay, so everything makes sense actually. If you have a much smaller spring with smaller stiffness, then again this is going to be high. What does that mean? The spring is pulling with much less force, so it takes more time to get back to the root. Alright? So whenever you have the solution, equation of motion of the system, you have to make sure that it makes sense physically. If all of these should fit in place, there should be no contradictions. Okay? So you have to think, you always have to put your findings to that. Well, I found this, and I know that tau is great, and the system is going to be slow. How can I make this system slow? By having higher B. Does that make sense? Yeah, it makes sense. Okay? You always double check your findings. Okay? So now we have a system like this. I use the example of mechanical system because it makes a little bit more sense. You can see it with your eyes, right? We're visual animals, as I said. An electrical system acts exactly the same way. For example, if you had a bx dot plus kx equals f external, then you just exchange them with their analog to move to an electrical system. What is the analog of the resistance, electrical resistance? What's the analog of x? The charge. What's the analog of the stiffness? It's the capacitance of the 1 over c, the inverse times q. What's the analog of this? Voltage external. Okay? So I apply voltage to an RC circuit. Alright, with ground here now. Alright, so this is R and this is C, and I give the external voltage. Alright, then I know that the capacitance is charging with Q, alright, with the same equation of motion. You're charging your phone, okay, by connecting it to an external voltage, alright, and its charge is rising, okay, and then you unplug it. So there's no external force, therefore your system starts decaying. Okay, it's always like that, all the systems. If the equation of motion is the same, then they act the same. If you know your analogy is right, then you know our one x, you know the other one x. Okay, that's the power of analogy. Okay. Alright. So we said that a mechanical example. I can show a system with a figure. When I draw that figure, everybody understands what I'm talking about. Everybody understands that it's a first order system in this class I'm holding. Alright? Not any common citizen outside. It's exposed to an outside force, okay? And its equation of motion is going to be its differential equation is going to be this, its equation of motion is going to be that. Okay? So you get a force balance, you get the differential equation, you solve the differential equation, you get the equation of motion. Like that. Force balance, differential equation, equation of motion. So that you can show the motion of the system with respect to time. Everybody understands it. I can also show the system as its differential equation. Dx dot plus kx plus equals f external, subject to x at time equals 0 is x0. Everybody understands. Okay? This is the second way of showing a system. I can also show the system by its equation of motion. X t, anytime t, the general solution of that equation is equal to x0 minus f external divided by k e to the minus k over b t plus f external divided by k. Alright? Another way of showing the equation. I'm showing the system. I can also show the system in terms of the block diagram. What does that tell me if I rearrange it? Bx dot plus kx equals f external, divide everywhere by b. Alright, take this on the other side. So x dot is equal to minus k over bx plus f external divided by b, also a differential equation. Okay? Just like this, the same thing. I show this as x dot equals 1 over tau, x plus If external over B, I know that's XSS. I'm sorry, not B, K. So I multiply this with K divided by K. Okay? So I have F external here, this term becomes F external divided by K times K over B.
Sorry.
Okay? Thank you. You understand that, right? K over B is the same thing. K over B being 1 over tau. It's going to be equal to F external divided by K, 1 over tau. So I write it like that here. F external divided by K times 1 over tau. Now I have 1 over tau here. I move all of them over there. Tau times x dot equals x minus x plus xxs. Okay, this is the form of the differential equation expressed in terms of a single parameter, tau, that describes the whole behavior of the system. How fast or how small it moves, when it reaches steady state, okay, everything. While it's changing its distance or state, recall, this is the transition state, and this is the steady state. Okay. So here we go. When the system reaches steady state, what does that mean? X is not moving anymore. That's the definition of steady state. If X is not moving anymore, what is X dot? 0. So minus X plus XSS is 0. So what is XSS? X. Alright, does it make sense? Yes, you always have to question yourself. Okay, does it make sense? So now what we have is, let's see, X, let's just show you like that. X dot equals minus 1 over tau X plus 1 over tau XSS. Okay? I know that 1 over tau XSS is F external over B anyways. Okay? It's the same. So, X dot on this line, which is the line that's showing the value of X dot. Now I need to find X. So what do I do? To find X from X dot, what do I do? I integrate. Okay, with respect to time. Now I have X. Okay? What do I do with X? I multiply it with 1 over tau. And now what do I do to that? Here I have X over tau. I have this without the minus. I have to add it to this. So minus plus XSS divided by tau, which is also equal to F external divided by K. Okay? So I can show the system as a block diagram now. In a simple form. This is the input. Alright, this is my system and integrator. This is my output dx, and I have a constant here, 1 over tau. Okay? I call this the pole of the system. The pole of the system, 1 over tau, okay, is actually equal to this. Okay? Or it's equal to that, whatever is in front of the x. That's the pole of the system. Okay? So I can represent my system as a block diagram. What does that show? The flow of information. X dot goes here, integrated comes out x, then I return back a feedback, okay, multiplied by a pole, and subtracted from the input. Okay? Actually, actually what I do with the input, A divided by B. Okay? If I put tau here, then I divide it by 1 over tau. I divide it by tau. So, block diagram, the figure, differential equation, equation of motion, all of these are system descriptions. Okay? Another way to describe the system is if I go into the Laplace domain. Then I have I have F external coming in here. Okay. I have the system and X is coming out. Or X star is coming out, whatever. So, if I did the whole thing, what's going to happen here? F external divided by B and the sign here, and we're going to have a whole here, and we're going to have a feedback line going back to the origin of the system to change the input of the system. This is the system. Now this input is not F external over B, but this. Okay, that is the same thing as that. And in the Laplace domain, this is going to be F external of S divided by B, going into the system, which is represented by an integral, which turns into a 1 over S now, and X over S comes out, and the 4 1 over tau. Okay? So I could show the block diagram in terms of time domain, in terms of complex domain, S domain. And later, two weeks from now, we're going to show the behavior of the system in frequency domain as well. Extremely important. Okay, we're going to go into that. Is it time? How many?
3 minutes.
3 minutes. Okay, so what we have here is the following. Bx star plus Kx is equal to F external. In Laplace domain, Laplace operator being linear, but now this is very important. Laplace operator being linear, I can do superposition. I can separate between each one. Laplace of Bx dot plus Laplace of Kx equals Laplace of external. Okay? Subject to say x 0 and equals 0. Laplace operator means superposal. Right? Now, Laplace operator means scalable. I can separate the scalars. B times L of x dot plus K times L of x equals L of F external. Okay? Now I can do the operation. What is this? B times, what is the Laplace transform of a derivative? S times x of s minus x0. Okay? If you remember that, you're going to learn. That's homework. Now, your first homework is going to be the Laplace of cosine omega t. Okay? The second solution of this equation, and the third one is going to be get the Laplace of x dot of t subject to x. Right? I want you to derive this expression plus k x of s have, huh?
It's 4.
I know, 2 more minutes. That's it. So we have ds x of s minus b x0 plus k x of s equals f external of s. Okay? Now, lo and behold, I can add the 2 x of s. Before this was apple, this was orange. Now both of them are bananas. Good. So ds minus plus k x of s is equal to f external of s plus b x 0. Alright, let's write it down. So what do I have there? ds plus k x of s is equal to f external of s plus b times x0, right? Okay. Now stay with me 1 more minute. What we're going to do is we're finding x, trying to find x. So I divide everywhere by ds plus k. ds plus k. Okay, I have x of s by itself. X of s equals 1 over ds plus k times f external of s plus 1 over ds plus k dx0. Okay? Or I can add these two up. Oh, my erasers are on this side. So what I have basically is I have an input, f external of s. I have another input, dx0. This is going into the system, this is going into the system. The system is 1 over ds plus k. And out comes my x of s. Okay? I show the system's transfer function. What is transfer function? How does the system transform the input into the output? Just like we said in the beginning. And notice here that x0 is also another input. Why? Because in order to create that, I had to give the system some force before the beginning of time. That is an input. Okay? So this representation shows that, goes to prove that x0, the initial condition, is an input in the past. Why is it in the past? Because it has no time in it. Time doesn't exist in the past. I started my time when I started to put the fx externals. That has the time. S being 1 over time. Alright? So, learn system representations. So far we have done 1, 2, 3, 4, 5, 6 of them. Okay, as a transfer function, as a force balance, as a differential equation, as an equational motion, and as a block diagram. And then the transfer function. Okay? And then do your homework. The third is, what was that? That. Okay? Do your homework. Get ready for the quiz next week. There is one. Alright, that's going to be up to you. If you learn all of these, there will be no quiz. Thank you for listening.